Okay, here's one more example for class 13. I don't know why I decided to put this many in here, but I did. This is also from Munson's Fluid Mechanics, and this is a hydraulic dredge. So what it's doing is it's sucking up a combination of sand and water, silt, and it's probably not environmentally friendly, by the way, especially because like all kinds of stuff at the bottom will often contain like contaminants and things, and now you're going to be shooting it onto the land. I don't know if that anybody wants to do that, but that's okay. Let's not worry about the mercury poisoning we might be causing. So we want to estimate the thrust needed in this propeller right here to hold this boat stationary. And we're going to assume that the specific gravity of the sand water mixture is 1.2. So there you go. All right, so I guess I'm going to start with my FBD. All right, so I have an FBD. And did I ever figure out what my mass flow was going to be? I think I maybe want to figure out my mass flow. M dot. It's going to be the density times the area times the velocity. And we know this velocity, and we know that's the dimension, and we know the specific gravity. So we can get M dot is going to be that 1.2 times water, and this is US units, so that's 1.94 is the density of water. So 1.2 times it is going to be the density of whatever this stuff is. And the area is pi over 4, and that's 2 feet diameter squared, and we're going 30 feet per second. So we're going to get ourselves a number I haven't calculated yet. So there you go. All right. 1.2, 1.94 times, and then go pi times 4 divided, that's 4 times 30 times. So 219.4 slugs per second is going to be our mass flow. And I'm going to move this down just a little bit so I can put my momentum diagram next to it. And I'm going to try my best to kind of do a control volume that goes all the way around this thing, and it cuts it off right there, and then up around this, and up around the antenna, something like that. So I'm going to draw, and I'm going to give myself a little bit of space because I need a little prop right there, and I'm going to put a force. That's going to be a thrust force, and that's a whole nother topic. There you go. I drew it kind of weird. All right, so that's looking like a snuffle up, I guess, kind of looking thing. But let's see. Let's try to draw the same thing over and over again. It looks like I'm a little teapot. A snuffle up, I guess, anteater looking thing. All right. So we got the weight of this. I got the buoyancy force. And I'm going to have some type of propeller thrust coming right there. Well, over here, we're going to have a m dot and velocity 1. Over here, we're going to have an m dot velocity 2. And so we say the sum of the forces on the control volume is going to be equal to the sum of the betas m dot v, and this is the out, minus the sum of the beta m dot v in, right? And we'll assume beta is approximately equal to 1, which is fine. This is a correction factor that the book we're using, Sengel, applies to these momentums in here because we're using average velocities in here, and that isn't going to be the equivalent to the average momentums. So in the x direction, that's all we're going to have here. We're going to have this the propeller's thrust that's required to hold this thing in place. You'll notice there's there's no force imbalance right here. So there's got to be something over here that balances over with there. That's the beauty of using two diagrams that you can rationalize. You could think of them as separate things that are taking place. Otherwise, their signs wouldn't make any sense, but now they do make sense and they balance out because you have two separate sides. You have the force side and you have the momentum side. Otherwise, it bothers me when they only use one diagram on top of the thing because you wouldn't be able to resolve the signs correctly. But this representation is better, I swear. So anyway, I can put this stuff in here. Of course, the only thing that matters is the stuff in the x direction, or a portion of this in the x direction, and that's 30 degrees right here. So I'm going to go ahead and put numbers in there because I'm tired. So I have 219.4 is the mass flow here, and is going out, and the velocity we established was going to be 30, but we're only going to take the cosine of 30 of this. And if I didn't make a numeric mistake, we would take 30 times and 30 cosine times, and we would sure enough get 5,000 right there, 5,700 pounds of thrust. And it needs to go boom like that direction. So there's 5,700. I really screwed that rectangle up. I guess I am tired. Tired of making videos for this. It's all right, I got to make them for next class as well. So right there, that is the answer. Cha-cha! I don't know why I included this example. I guess I kind of liked it. That's why. Yeah, sure. That's the reason. So more to come for class 14 coming up. And we can stop.